Now we are going to start discussing the singularities and zeros of analytic functions. Okay. In particular, we will answer the following questions. First of all, we will of course define what a singularity is, or when do we call a function singular at a point. Okay. Then we will talk about some peculiar types of singularities, including the isolated singularity, which is often called as the pole. Okay, so isolated singularity refers to pole. Okay, and then we'll talk about terms like order of a pole, and if the order of a pole is infinite, then we call that singularity as an essential singularity. Okay, now all these things come or can be defined using the Laurent series. So it is essential to know what Laurent series is. In particular, the two parts of the Laurent series, the regular and or analytic, and the principal or singular part. Okay, then like we have removable continuity, we have something what we call removable singularity, and we are also going to take the same example that we take there. Okay, sin x upon x or sin z upon z here, and then we will mention two theorems. We will not prove them, but we'll mention the statements with examples and explanation, and this includes the famous Picards theorem. Okay, fine. So as far as the singularities are concerned, these are the topics that we will cover. And now let us talk about zeros. Okay, now by definition, zero means that value of the independent variable for which the function takes the value 0. Okay, for example, if I have the function x squared minus 4, then there are two zeros of this function, plus or minus 2. Okay, and by the very definition of the 6 trigonometric functions, well, 4 of them, not the cosec and sec, those functions also have infinitely many zeros. Okay, sine is 0 when x is integral multiple of pi, and cos is 0 when x is an odd multiple of pi by 2. Yes. Okay, fine. So we'll talk about zero of an analytic function, and like we have order of a pole, we have order of a 0, and we have isolated singularity. We also have the isolation theorem for zeros. Okay, now at last we'll talk about the connection between the zeros and the poles, and the reason is quite often we encounter situations where the function is not defined because the denominator of the function consists of terms which may become 0 for some values of z. For example, consider this function whose Laurent expansion we have just found out, f of z equal to z upon z squared plus 1. Okay, now the points where the function is not defined is z equal to plus or minus I. So these are singularities of the function. Okay, and these also are the zeros of the denominator. Right? So these are closely connected to each other, the zeros and the singularities. Okay, and we also have a theorem for that. We'll see that now. Okay, now let us start discussing the singularities and the zeros. We'll first discuss the singularities, and then we will extend our discussion to zeros. Okay, now this particular discussion is going to have a lot of new terms and their definitions. Okay, at times this may appear confusing, but yes, this is how things are in the calculus of complex variables. Okay, let us start discussing singularities. So when do we call a function singular? A function f of z is called singular at a point z0 if it is not analytic at z0. Now please note that here we are not saying that a function is singular at a point z0 if it is not defined, because when we say not analytic, it actually includes those situations where the function may not be defined, but it also includes those points where it is defined but is not analytic. Okay, for example, we have discussed f of z equal to z bar. Okay, we have seen that this is analytic nowhere, right? So although it is defined everywhere, it is not analytic. So I would say every complex number is actually a singularity for the function z bar. Okay, so please note the definition of singularity carefully. It is not the points where the function is not defined. It is those points where the function is not analytic, which includes the points where it is not defined. Okay, examples. Example number 1, f of z equal to z upon z squared plus 1. Because it is a rational function, the denominator and the numerator are analytic everywhere. Therefore, this rational function will be analytic everywhere except for those points where the denominator is 0. Okay, so clearly the two singularities are z0 equal to I and minus I. Okay, let's now consider a bit different function. This time a composite function g of z, which is tan of 1 over z. Inner function is 1 upon z. Okay, now this function will not be defined at 0 because the inner function is not defined there. Yes, and if 1 upon z is a non-zero number, still we do have possibilities where the function is not defined, and this time it is because of the outer function. Okay, so if we consider z0 to be 2 by pi, 1 upon z0 will be pi by 2, which implies that the function is not defined. Okay, so clearly it is not analytic. Okay, so let me repeat. Singularities are those points, those complex numbers where the function ceases to be analytic, which covers all those points where the function is not defined. Okay, now let us start discussing the types of singularities. Let's talk about isolated singularity first. So if we have a function f of z, okay, and the singularity is z0 where the function is not analytic, we call it an isolated singularity if the function f is analytic on the deleted disk 0 less than mod of z minus z0 less than r for some r greater than 0. Okay, and the word pole refers to isolated singularity. Okay, now by the very name isolated singularity, we understand that there isn't any other pole there isn't any other singularity, I would say, in some neighborhood of z0. Okay, this is the other way of defining isolated singularity, and the word isolated should be, well, it conveys everything that the whole thing wants to convey. Okay, so let us now talk about two examples which we already discussed. One of them will have isolated singularities and the other one will have one non-isolated singularity. Okay, all right, so I think for f of z equal to z upon z squared plus 1, it is very easy. Okay, already having identified its singularities, we now note that z0 equal to I is a number which lies on positive y-axis or positive imaginary axis 0, 1, and z naught equal to minus I is a complex number which lies on the negative imaginary axis. Okay, so if we now consider two deleted disks, meaning we will not consider the centers, one centered at 0, 1, and you can take any radius less than 2. Okay, and same thing with this. Within these two disks there are no other zeros, well, no other singularities, right? Yes, so these are isolated singularities, or we will call them as poles. Okay, now let us discuss the second example, the composite function tan of 1 upon z. Okay, now as I said earlier, this function has singularities because of the outer function as well as because of the inner function. Okay, let us first talk about the singularities of the outer due to the outer function. Okay, and these start with 2 by pi, which is the situation that we have already discussed. Okay, now 2 by pi, 2 by 3 pi, 2 by 5 pi, 2 by 7 pi, this is a sequence. In fact, it is a harmonic progression. Yes, harmonic progression. Okay, now these are the singularities which are isolated, right? These are isolated singularities because the difference between them is always non-zero. Okay, whereas if we talk about the singularity due to the inner function, that is 1 upon z, which is z naught equal to 0, this is not an isolated singularity because closer you go to 0, okay, because of this decreasing sequence, you will always be able to get yet another singularity within your radius of the disk. Okay, which means no matter how small you consider the neighborhood to be, there will always be another singular point in it. Okay, now that singular point that you are considering is going to be a regular singularity, isolated singularity as far as the function tan of 1 upon z is concerned, but 0 itself is a singularity, so this this violates the definition of isolated singularity, and therefore the function tan of 1 upon z has one non-isolated singularity and infinitely many isolated singularities. And the only non-isolated singularity is the number 0. Okay, I mean, if you wanted, you could have considered the negative terms as well, minus 2 pi, minus 2 by 3 pi, and so on. Okay, all right, so having discussed the isolated singularities, let's now go to the essential singularity. Okay, and this actually requires us to know the Laurent series. Okay, so let me remind you of the Laurent series. Now I will just write down the conclusion. Please note that the expansion is valid only in the region of convergence. Okay, so this consists of two series. Okay, the first one is summation as n runs from 1 to infinity bn into 1 upon z minus z naught to the power n, okay, which is known as the principal part or the singular part. And the next one, let me write it in the red color, an into z minus z naught to the power n. Okay, now what we will use to define the order of a pole and the essential singularity is the principal part. Okay, because it consists of the coefficients bn. Okay, so here goes the definition of order of the pole. If bk is not equal to 0, and for all values of n which are greater than k, if bn is equal to 0, then we say that z0 is a pole of order k. Okay, and if an infinite number of the bn's are non-zero, we say that z0 is an essential singularity, or we also call it pole of infinite order. Okay, I mean the definition of pole of infinite order follows from the pole of order k. Okay, meaning we will always have finitely many terms in the Lorentz series expansion of those functions around the pole z equal to z0. We will call them to be pole of order k. And if we have infinitely many terms in the principal part or the singular part, we will call it an essential singularity. Okay, let's talk about examples. We will consider the function f of z given by z plus 1 upon z, whose Lorentz expansion we already know. It is 1 plus 1 upon z, and the center is z0 equal to 0. Okay, and about this point we have expanded f of z. Okay, now note that its Lorentz series consists of two terms, a0 from the regular or analytic part and 1 upon z from the singular part. Okay, and what is b1 here? b1 is equal to 1. Yes, and for all other values of n, bn's are equal to 0. Okay, and therefore we say that z0 is a pole of order 1 because b1 is equal to 1, and for all other values of n, bn's are 0. And if we have a pole of order 1, we often call it a simple pole. Okay, fine. Let's talk about example 2 now. In one of our previous problems, we considered the Maclaurin's expansion of e to the power t, right? So this function is h of z equal to e to the power 1 over z. Again, the center is 0. So this time you observe that the Maclaurin's expansion produces e to the power 1 upon z as 1 plus 1 upon z plus 1 upon 2 factorial into z squared plus 1 upon 3 factorial into z cube and so on. So what do you observe here? Bn, okay, is actually 1 upon n factorial. b1 is 1, b2 is 2, well, b1 is 1 upon 1 or 1, b2 is 1 upon 2, b3 is 1 upon 6 and so on. So all bn's are non-zero. Okay, and if an infinite number of bn's are non-zero, we say that z0 is an essential singularity, and therefore for the function e to the power 1 upon z, the number 0 is a pole of infinite order or an essential singularity. Okay, fine. Yeah. The last term that we are going to discuss from singularity, apart from the theorems, is removable singularity. Okay, now this resembles the removable discontinuity part. Okay, so we are going to consider a function, let's call it p of z, as sine of z upon z. Okay, and well, this function is not defined at z not equal to 0, we know that, and because sine z and z are analytic everywhere, the point where this function ceases to be analytic is the point where the function is not defined, and that is 0. Okay, now sometimes the function sine z upon z is called as the sinc function. Okay, sine and then c. Okay, now what is a removable singularity? if all the bn's are equal to 0, then it is a removable singularity. In short, it shouldn't have any principal part in the Laurent expansion. About the pole, well, about the singularity. Okay, all the bn's are 0 means the same thing, no principal part. Okay, now again let's take the help of the Maclaurin's expansion of sin z. Okay, and because the smallest power there is z and the largest power in the denominator is also 1 or z, this leads to the cancellation of z. Okay, and this then leaves no powers of z which are negative integral powers, so which means all bn's are 0. Yes, and hence it is a removable singularity by definition. And how can we remove it? We can remove it by redefining sinc z as 1 at z0. Okay, and then it becomes analytic. Okay, so we have now seen two situations. Okay, if all bn's are non-zero, we call it essential, and if all bn's are zeros, we call it removable singularity. Okay, so in your examination, a 1 or a 2 mark question may come asking you to define the essential singularity and the removable singularity and stating the difference between these two types of singularities. Okay, for essential singularity, you have to have infinitely many terms in the principal part. Okay, yes, and in this case you are supposed to have no principal part at all. Okay, fine. See, in the essential singularity, let me put it in this way: there may be terms, there may be bn's which are 0, but an infinite number of bn's must be non-zero. Okay, for example, if b1 is 0 and all other terms are non-zero, all other bn's, it will still be called as an essential singularity. Okay, but for this, all bn's should be equal to 0. Okay, and we have seen an example of that. Fine. Now we are going to see two theorems. The Picards theorem will follow. Let's first read the statement and try to understand what it is saying. This theorem says, if the function f of z is analytic and has a pole at z0, meaning at this point it is not analytic and this is an isolated singularity, okay, then the modulus of f of z tends to infinity as z tends to z0 in any manner. So irrespective of the path chosen on the complex plane, as you start approaching z0, the absolute value or the modulus of the function will always approach infinity. Okay, and for this let us consider the function as 1 upon z. The only point where this is not analytic is the point z equal to 0. Okay, and what is the modulus? 1 upon z's mod will be 1 upon root of x squared plus y squared, and we know now that if z tends to 0, both x and y tend to 0, and because we consider the positive root, only the positive root, this limit is infinity. Okay, so if f of z is analytic and has a pole at z0, then as you start approaching z0, the values of the function become large in modulus. Okay, that is what this theorem is telling you. Now let us go to the Picards theorem. Okay, the Picards theorem has 3 things given. Okay, I mean these 3 things should be there so that we can have the conclusion of the Picards theorem satisfied. Okay, so we have an analytic function f of z, first thing. Second is we have an isolated singularity as well as an essential singularity. Okay, so this singularity has to be isolated, meaning in some neighborhood of that there shouldn't be any other singularity. Okay, and it also must be essential singularity, means the Laurent series expansion of f of z about z naught should have infinitely many terms in the singular part, okay, or in the principal part. Okay, and then of course we'll consider an arbitrarily small neighborhood, let's call it epsilon neighborhood of z naught. Okay, so epsilon is the radius and let us call the neighborhood as n. Okay, and the conclusion of the Picards theorem is that f of z takes on every value, okay, with at most one exceptional value in n. Okay, now let us just try to understand what this means with the help of an example. Okay, we have already talked about this earlier. This function is e to the power 1 over z. Okay, first let us make sure that it is analytic. It is an analytic function. Yes, it is analytic everywhere except at the point z equal to 0. Is the singularity isolated? Yes, this is the only point where the function is not defined or not analytic, so it is isolated. Correct. So this requirement is fulfilled. Is it an essential singularity? It is. Okay, I mean, you may recall the Maclaurin's expansion of e to the power 1 upon z and e to the power t, where t is 1 upon z, and conclude that all bn's are non-zero. For an essential singularity, infinitely many bn's should be non-zero. So this is clearly essential singularity. Yes. Okay. Now you may note that in this case, the following two things apply. Suppose z is purely, suppose z is real. Okay, let's not call it purely real. Suppose z is real. Okay, then we know that there is no need to consider the imaginary part, so we can now talk about our old x-axis. Okay, and as you approach 0 from right, old right hand limit, 1 upon z approaches infinity, which implies that the limit of the function, which is e to the power 1 upon z, tends to infinity. Okay, so we have now made sure that it takes every positive real value at least. Okay, now let us talk about the left hand limit. Okay, we know that if z approaches 0 from left, 1 upon z will approach minus infinity. Okay, and our function, which is e to the power 1 upon z, will approach 0. Okay, fine. Now if z is purely imaginary, that means if you find the limit of f of z as the complex number z is on the imaginary axis, then you can show that this function doesn't have any limit. Okay, fine. So now what we are going to do is to check for the conclusion f of z takes on every value with at most one exceptional value in the neighborhood. We are going to consider the following. Okay, we are going to use the complex exponential form of the complex number. Okay, so let us assume that e to the power 1 upon z is in the form u plus iv, where z is in the form x plus iy, but let's not use u plus iv, let us use uppercase r times e to the power I alpha. Okay, and for z let us use lowercase r times e to the power I theta, the conventional notations. Okay, now is it possible to find r and alpha? Of course we can. Okay, so write e to the power 1 upon z as e to the power 1 upon r e to the power I theta. So when that e to the power I theta goes to the numerator it becomes e to the power minus I theta. Okay, now what can you say about the modulus of this result? Okay, the modulus is going to be e to the power cos theta upon r. Yes. Okay, there shouldn't be any hesitation in saying that. Yes, e to the power cos theta upon r, because the other thing is e to the power I into minus sine theta upon r, which is alpha. Okay, and the modulus of that part is going to be 1. Okay, let me put it in this way now. This can be written as e to the power cos theta upon r multiplied by e to the power I into minus sine theta upon r. Okay, so no matter what values theta and r have, e to the power I theta is always, or e to the power I into any number, any real number, is always going to have the modulus 1. Okay, so this then gives us the following two results. The modulus of e to the power 1 upon z is going to be e to the power cos theta upon r, where r and theta are the modulus and amplitude of the input, okay, or z, and the argument of the function or argument of u plus iv is now going to be negative sine theta upon r. Okay, let us call it alpha. Okay, now to show that this function takes on every value except for one possible exception, we proceed as follows. Okay, we try to get the argument and the modulus. Okay, first thing is, let us obtain tan theta, which is the easier thing to obtain. Divide the second equation by the first. Okay, first you shift r there and multiply by minus 1, so you'll get sine theta as minus alpha r, and this time here you take log because you want cos theta and r not in the exponent. Okay, so r times log r will be cos theta because log of e is 1. Okay, and then you can divide sine by cos, so tan theta will be minus alpha r upon r ln r, and then you can just cancel r because r can never be 0 in this case. Okay, so we have got tan theta, but that's not important. What's more important is the next part. Okay, square and add both things. Okay, sine squared theta plus cos squared theta will give you 1. Yes, now sine squared theta here is alpha squared r squared, and cos squared theta here is r squared ln r squared. Okay, which means r squared is now equal to 1 over ln r raised to 2 plus alpha squared. Yes, now pay attention. If we want very small or arbitrarily small neighborhood of the number 0, what we would like to do is we would like to have r 0 or a situation where r tends to 0. Now if r tends to 0, I mean if we want r tend to 0, what can we say? Okay, we can say that let's not change r, okay, uppercase r. Let us just keep on adding integral multiples of 2 pi to this, which will make sure that tan theta doesn't change, but r will keep on decreasing. Okay, so if we let alpha replaced by alpha plus 2n pi, it will make r smaller and smaller and smaller. Okay, so that proves that e to the power 1 upon z takes every value except 0. Yes, and that proves, or that verifies, the Picards theorem. Okay, fine. So this was the discussion as far as the singularities are concerned. Let us now go to zeros. Definition: a zero of an analytic function f of z in a domain D is a complex number z naught such that f of z naught is equal to 0. Okay, now the definition of 0 is very simple, but we are defining zeros only for analytic function, so please keep that in mind. So whenever the function becomes 0, the input is said to be, or is called as, a 0 of the function. Okay, now just like we had order of pole, we also have order of a 0. Okay, so if we call order of a 0 to be n, if condition number 1, not only the function f but also its derivatives till the order n minus 1 are 0 at z0. This is important. At z0 all these derivatives should be 0. However, the very first derivative where the function is non-zero, or function's value is non-zero at z0, if it is dn, then the order of that 0 becomes n. Example, question 1. Suppose we have the function f of z as 1 plus z squared. Clearly this has zeros at two different points, plus or minus I. Yes. Let's now calculate the derivative. Okay, so here d is equivalent to d by dz. Okay, where z is the complex number. Okay, the complex variable. So derivative will be 0 plus 2z. Yes. What is the derivative's value at I? 2i, not equal to 0. Derivative of the value of the derivative at minus I, minus 2i, again not equal to 0. So both these zeros have order 1 because the first derivative itself is non-zero. Okay, n equal to 1 for question 1. Okay, let us see one more example. Okay, so this function is 1 minus z to the power 4 to the power 2, the bracket to the power 2. Clearly this function has 4 zeros, positive and negative 1 and positive and negative I. You have solved these questions using the de Moivre's theorem in your complex numbers chapter. Okay, now to find the order of these zeros, let us expand the function by using a minus b bracket squared. It will be 1 minus 2z to the power 4 plus z to the power 8, and let us start differentiating. Okay, so derivative will be 0 minus 8 into z cube plus 8 into z to the power 7. Yes. Now if we take 8z cube common from both the terms, the first term will be minus 1, 8z cube, so the second term will be z to the power 4. And because for all our zeros their fourth power is 1, the value of the first derivative is going to be 0 for all these zeros. Okay, now let us go to the second derivative. Derivative of the first term, minus 24z squared, and here we have got 56 z to the power 6. Okay, if we take 8z squared common from these two terms, then you are going to get minus 3 as the first term in the bracket and 7z to the power 4 in the second. Okay, now z to the power 4 is 1. Okay, so this term is definitely not going to be 0, and so is 8z squared. Okay, so the second derivative is not equal to 0 for all of them, which means n value, or the order, is equal to 2 for all the zeros of this particular function. Okay, so n equal to 2 for question 2. So you may get a question in the examination asking you to compute the order of the zeros. Okay, fine. Now we are going to see two theorems. Okay, one is an analogous theorem to the isolated singularities, and the other one is the one which connects the zeros and the singularities. Okay, now this theorem says the zeros of an analytic function which isn't 0 everywhere are isolated, if at all the function possesses zeros. Okay, so the first requirement is that the function has to be analytic. Okay, only then you can apply this theorem. Okay, and the theorem says that the zeros of this function are isolated. What does it mean? It means that if z equal to z0 is a 0, okay, then you can actually come up with a neighborhood okay, which will not include any other zero. Any other zero. So it by definition then isolates that particular zero. Alright. Okay, so let us consider the same example that we have already discussed, f of z equal to 1 plus z squared. Okay. Now for this, there is no other zero in the neighborhood of the 0 z not equal to I. Yes, because the other zero, which is negative I, okay, the distance between these two zeros on the complex plane is 2 units. Okay, so you can consider the radii to be any positive real number less than 2. That should be enough to get the value of R, and hence the theorem gets verified. Okay, which says the zeros of an analytic function are always isolated. Okay, all right. Now the last theorem, okay, which is the theorem which connects the poles or isolated singularities and zeros. And if it is an analytic function, we have already seen from the previous theorem that the zeros are isolated too. Okay. Now what does the theorem say? The theorem says that if the function f of z is analytic and if it has a zero of nth order at z0, then 1 over f of z has a pole or an isolated singularity of the same order at z0. Okay, so here you should recall or remember what do we mean by a pole of nth order. Okay, a pole of nth order means the associated coefficient of the Lorentz series is not 0 and all other coefficients are equal to 0, which have a subscript greater than n. Okay, all right, so that is what we mean by pole of order k or order n. All right, so let us now discuss the theorem in the context of the question, or in the context of the function f of z equal to sec of z. Okay, now sec z is 1 upon cos z. Yes, so clearly the function sec z has poles wherever cos z is equal to 0, right? Now cos z is equal to 0 at z equal to pi by 2, we know that. Okay, and what is the derivative of cos z? Minus sin z. Now minus sin z is not 0 at pi by 2. Okay, it produces the value minus 1, which is clearly not equal to 0. So according to the theorem, the 0 of order 1, okay, so according to the theorem, pi by 2 is the 0 of order 1 for cos z, and hence it becomes the pole of order 1 for its reciprocal, that is sec z. Okay, so if f of z is analytic, okay, in this case cos z, okay, and if it has a 0 of nth order, then its reciprocal must have a pole of the nth order at the same location. Okay, all right. Now what does the Laurent expansion has to say for this? Okay, you can actually obtain this particular I would say Laurent expansion. Okay, sec z is given by 1 upon z minus pi by 2 plus 1 upon 6 into z minus pi by 2 plus all positive integral powers of z minus 2 with their appropriate coefficients. Okay, now note that b1 is equal to 1. There is no b1 here, which means it is 1. Okay, so b1 is equal to 1 and all other bn's are equal to 0 for the Lorentz series expansion of sec z about z equal to 0. Yes, which means if bn is equal to 0 or if bn's are equal to 0 for all values of n which are greater than 1, it must be a first order pole or what we call a simple pole, because it is a pole of order 1. Okay, so to summarize, if you have a function and its reciprocal, if you know that the function is analytic and has a 0 of nth order at some point, the reciprocal of that function will have a pole of the same order at the same location.